Sorry, we'll do question number 16. My mistake. Start with the discussion of question number 16. So in this, you have this situation. You have an elevator which has got a pulley, but the pulley is fastened by a spring balance kind of weighing machine onto the ceiling of the elevator. And of course, there are two blocks which are arranged into an Atwood machine kind of arrangement. So simple pulley system, but the pulley is basically attached to the ceiling with a spring balance. So the spring balance reads the tension in this part where the pulley is attached at the axle. So that is the reading that the spring balance gives. Okay. And these masses are, let's say, M1 and M2. Now the other thing is that the whole pulley itself, the whole elevator itself is going up with an acceleration. It is given to us as g by 10. And the masses are given to us as 1.5 kilograms and 3.0 kilograms. Okay, Bhargav, we'll discuss 15th also later. Okay, so we have to find the reading of the spring balance. Okay, so this thing over here, excuse me, it's a spring balance. So we have to find the reading of the spring balance. So to understand this question, we have to first talk a little bit about the working principle of a spring balance. How does the spring balance give us the reading? What happens is in the spring balance, internally there's a spring that responds to the amount of tension that the spring is being pulled by. And accordingly, the spring extends and it gives you the reading of the tension in the spring. But only thing is that the reading is not given in newtons, then it is given in kgs, where the value of the reading in kgs is actually the tension divided by g. So I'll explain this, what it means. Okay. So we'll talk about the working principle of a spring balance first. So what happens is whenever you suspend an object using a spring balance, so internally inside the spring balance, there is a spring like this. And that spring is attached to the ceiling. Okay, and the spring is attached with a pointer. So the pointer gives you a reading. So when we now suspend some weight over here, we suspend some mass m. Now generally if we are in the inertial frame, if this whole situation is in the inertial frame, then we can see that the tension that is acting over here, okay, that tension in the spring is equal to kx, and that is equal to the weight of the block. Okay, so the reading of the spring balance, the reading is basically the position of the pointer. So what happens is the position of the pointer that is proportionate to the extension of the spring. The spring जितना extend हो रहा है वो pointer उतना नीचे जाएगा, or the lesser the spring is extended, the more the pointer will be above. So for example, if the spring is in natural length position, the pointer shows you the 0 reading. If the spring is at an extension comparable to x, or at an extension of x, let's say, the reading of that will be proportional to x. Now if we increase the extension to 2x, the reading will become double like that. So that's what we mean, that the position or the reading of the pointer is proportional to x. And from here you can see that x is proportional to mass m. So ultimately that is what is used. So the reading is given in kgs. Okay. So basically that reading is basically what it is, x equal to mg by k, but it is expressed as some constant into m, and that constant, as you can see, is g by k. So this reading is now given in kgs. Instead of giving it in meters, it is given in kgs. Understanding? So the value of the scale is calibrated in such a way that the reading x is, this x quantity is proportional to the reading, and the reading is expressed in kgs. Okay. So for example, if it is like, if you suspend for m equal to 1 kg, Okay, what will happen is that the value of x will be g by k. So the reading it will show you, which is proportional to x, will be equal to 1 kg. Then if I increase the mass to, let's say, 1.2 kg, the reading it will show you now, it will be 1.2 g by k. I mean, the value of x will be 1.2 g by k for a mass of m2. So what it will do is automatically it will, because the extension has become 1.2 times this, so the reading it will show on the scale will be 1.2 kg. Now, if I change the mass which is suspended to m3, which is, let's say, 5 kilograms, so now the reading, the spring's extension will become 5g by k. So that is 5 times this initial value. No? So accordingly on the scale, it will show you the reading in kilograms of 5 kg, because it's calibrated accordingly, that when x is g by k, the reading is 1 kg. So when x is 5g by k, the reading it's showing is 5 kg. So hope this concept is clear to all of you. This is the principle on which the spring balance works. Okay, there's a working principle of the spring balance. Somewhat similar to it is the working principle of a weighing machine also. Like the floor standing weighing machine that you have, that's there in the previous question also. So in that, what happens is when a person is standing, internally inside this weighing machine, there's a spring. So the spring, internally inside it, there's a spring. And according to the normal reaction that the person is applying on this, that spring shows an extension, sorry, a compression of that normal reaction, where X will become the compression of the spring. Okay. And normally in inertial frame, when the system is at rest, if the person's mass is m, then the normal reaction is equal to mg, because the person will be applying a downward normal reaction. This thing will be applying, the surface of the weighing machine will be applying an equal and opposite upward normal reaction. So what happens is that the normal reaction is equal to the weight. That is the assumption, assuming that there's no other force. So X becomes equal to N by K, which is equal to mg by K. So again, you can see X is proportional to M. So the reading is expressed in kgs because it's proportional to M. So both of these, devices which are used to measure the mass of an object, are the working principle is basically the springs physics. The physics of the spring, that either when you load the spring from above with a normal reaction force, it gets compressed, and the compression is proportional to the amount of the force, and therefore proportional to mass. Or when you suspend a block using a spring, then the spring undergoes an extension, and now it is extended, whereas in this case the spring was compressed because of the normal reaction acting from above. So it is L minus X. So in either case, the position of the spring, and therefore the reading of the machine, whether it's a spring balance weighing machine or a floor standing weighing machine, it is proportional to X. Okay, and that means the reading it will show will be proportional to the mass in normal circumstances. That is when the object is at rest in inertial frame. Of course, we'll see in the previous question that is not happening. So it's going to show a different kind of reading. So Bhargav, hope this concept is clear to you, the principle of the weighing machine and the spring balance, because that is what is being used in both these questions, 15th and 16th. Okay. So the spring balance concept is clear, no? Okay. So now let's see what's happening in this particular question. So coming back to that diagram, I'll just pick up that diagram from here. So abhi kya ho raha hai? The spring balance will show a reading which is proportional to the tension in the spring, na? Or the extension in the spring. So that will depend on what? That will depend on the reaction force tension at the axle of the pulley or at the hinge of the pulley. I'm coming to that. I'll explain. So here now see what is happening is that this will be applying some kind of tension. Okay. So that tension, let's say, is T naught. So that tension T naught is equal to Kx of this spring balance. Okay. So the reading of the spring balance is proportional to X, which means it's proportional to that tension T naught. Okay. So in fact, the proper reading will be in kgs. So it will be equal to T naught divided by G, because T naught is equivalent to mass into G. So whatever tension in newtons divided by acceleration due to gravity in meters per second square, that will be the reading that the spring balance is showing. Okay. This will be the reading for the spring values. So now all we have to do is for the given values of M1 and M2, which I think were 1.5 kgs and 2 kgs if I'm not mistaken, we have to find how much this tension is. This tension, okay? And remember that this is a massless pulley, or it's a light pulley. So we have to take massless and smooth pulley. Okay. So now let's see what's happening is with respect to a person who's inside the lift, if this one has a downward acceleration A, this one will have an upward acceleration A only because the pulley will be at rest. Okay. And there'll be a uniform tension in this whole thread at every point, which is T. Okay. So what will happen here is that with respect to the reference frame of the elevator, with respect to the non-inertial reference frame of the elevator, okay, the pulley is stationary in that frame, no, because it's fixed to the ceiling. So pulley is at rest, and M2 is having a downward acceleration of A, M1 is having an upward acceleration of A. So what we'll do is that we will solve the free body diagrams of M1 and M2 blocks in this non-inertial frame, okay, and find that tension T. And once we have found tension T, from that our tension T naught in that spring will become 2T, because what is happening is that the axle of the pulley is being pulled up with that tension T naught, which is Kx in the spring, and the spring is, I mean, the pulley is also being pulled down by the thread on either side with tension T and tension T. Okay, so since the mass of the pulley is zero, no, because it's massless, so therefore what should happen? Net force on it should be zero. So that's how we get this. That this should be equal to 2T. So once you got 2T, from that we can get the reading of the spring values. So the concept of the question is clear to all of you. Okay. So if you haven't done this question, please try it out using this now. So I've told you what to do here. You have to make the free body diagrams of M1 and M2 in this non-inertial frame, first of all. And once you've done that, from the free body diagram equations, you have to solve for T, the tension in this thread. And once you got that, just double that. That is nothing but the tension in the spring. And that will give you the reading of the spring balance. Is this clear, people? Bhargav and Harsh, is this clear? Okay, so just try to solve the equations. You haven't done that before. I will put up the free body diagram and the equations in a minute, but I want you to try and get it right yourself. Okay. Yeah, Priyanshu, I will send the recording of session 8 and the notes also. The recording is yet to be uploaded, so I'm just waiting for that to happen. But today it will get done. Okay. Okay, so let's see the free body diagrams in the non-inertial frame. Just making that. So in the non-inertial frame of the elevator, that frame itself is going up with an acceleration of a naught. Okay, and a naught is given to us as g by 10. M1 is 1.5 kg, M2 is 3 kgs. Okay, so in that frame, what is happening to M1? It is going up with an acceleration a, and what is happening to M2 in the same frame? It is coming down with a. So a is the acceleration of M1 or M2 with respect to the stationary pulley in the elevator's frame. And by the way, that is which type of frame? It is a non-inertial frame. So the first thing in a non-inertial frame, you have to show the pseudo force. So this will experience pseudo force M1 A naught, and this will experience pseudo force M2 A naught. So these are your pseudo forces. But apart from that, they will both experience tension. Okay, and of course, they will both experience weight of their own. M1G for this one, M2G for this one. So these are the three forces in the non-inertial frame. So for the block M1, we will have the equation T minus M1G minus M1A naught is equal to M1A. And for the block M2, we will have M2G plus M2A naught pseudo force, that is minus T is equal to M2A. So these are the two equations, and tension is unknown, A is unknown. A naught is known to us, G by 10, and M1 and M2 are known to us. So substitute these values and solve for what? Solve for T. You don't need to solve for A right now, because what we need is the reading of the spring balance. So that will come from the value of T. Right, so hope you're understanding this, people. Just solve this quickly. Okay, so people, let's look at the solving part quickly. Anybody's got the answer, you can tell me. Okay, so the first equation, when you substitute, you will get T minus 1.5 G plus G by 10 is equal to 1.5 A. And the second equation, when you substitute this thing, you will get 3 into G plus G by 10 minus T is equal to 3A. Okay, or this is telling you 3 by 2A is equal to T minus 3 by 2 into 11G by 10. Like this. Okay, and this is telling you that 3A is equal to 3 into 11G by 10 minus T. Okay, so just comparing these two equations, now you can see that 3A, which is from the second equation, 33G by 10 minus T, is double of the right hand side on this side, which is T minus 33G by 20. Okay, so 33G by 10 . So T is going to become 33G by 5. So therefore, which is the spring force, that is 2T. So that is 66G by 5. Okay, so the reading of the spring balance will be equal to Kx divided by G in kgs. So it will be 66 by 5, or wait a minute, it seems to me I made some mistake in the calculation. Let me just check. Oh yeah, there's a 3 here. I missed this out. This is 3T. Okay, so this will become, T will become 11G by 5. My mistake. Okay, so this should be, okay, so this should be how much? 22G by 5. Okay, so this reading should become 22 by 5, which is the given answer, 4.4 kgs. So first of all, let me know if there's any issue with the equations, if you understood the equations or not, how we got them. Then the solving part is easy. I'll explain how it's coming. But just see from the free body diagram how these equation 1 and 2 has come. First, make sure you understand this. Then here I've just substituted the values of M1 and M2. I put M1 as 1.5 kg or M2 as 3 kg. Okay, and of course A naught as G by 10. So I've substituted that. And then this is just solving of this. So what I'm doing is now from equation 1 and 2, I'm keeping the left hand side the same. So 3a on this. So this will have to be multiplied with 2. So 3a from this is twice of this whole thing. So that's how we got this. So hope the solving of this is clear. So finish with this and start with the free body diagram in question 15. I'll explain the same. 15 also. So in 15, do the same thing. Make the free body diagram of the person in the non-inertial frame of the lift, of the elevator. Now that elevator one time will have an upward acceleration, one time it will have a downward acceleration. Okay, so both the things you have to consider. Because one time it is going up with acceleration, then it's decelerating. So when it's decelerating while going up, the direction of the acceleration vector is downwards. So initially it's accelerating while going up, so the direction of the acceleration vector is upwards. Later it is decelerating while going up, so the acceleration vector should be downwards. So that's the concept in the 15th question. Just go through and try it out. Okay, Harsh, I'll show you the working of the spring balance and the weighing machine, both the things. Okay. Yeah, Jay, I will come to question 33 and 35 very soon. Okay, so Harsh, are you clear with the working of spring balance and weighing machine now? Both these are clear now? Okay. Now let's quickly come to the free body diagrams in question 15. Very similar concept, but much less complicated, because just have a person standing on a weighing machine inside an elevator. So we'll consider three situations for the person inside the elevator. One is when the elevator is going up with acceleration. Then the second is when its speed becomes constant. And third is when while going up, it is decelerating. Okay. So one is when it's going up with acceleration. Okay. So it is accelerating upwards. Okay. The other is when its speed becomes constant. It's going up with the uniform upward motion. Okay. And the third case is when it is going up with some velocity, but it is decelerating. So its acceleration vector is downwards. So in this third situation, the elevator is decelerating while moving upwards. Okay. So the three situations you have to understand how that is going to affect the reading of the weighing balance, okay, while moving up. Okay. So now in each case, there is a person standing of the same mass inside the elevator. Okay. So he is at rest standing on the weighing machine. Okay. So in this case, when you see the elevator is which type of reference frame? It is a non-inertial frame, okay, which is going up with A naught. So now when you make the person's free body diagram, on that person there is what all force? There is pseudo force. Okay. There is this true weight mg, and there is normal reaction acting, let's say N1. Okay. So in this case, what is happening? N1 equals to, and he's at rest now in that frame. In the non-inertial frame, he's at rest. So N1 is equal to mg plus ma naught. So this is when the normal reaction will be more than his true weight. This is that situation where the normal reaction is more than his true weight. Okay. And the second picture, what is happening? The elevator is going up, but with uniform velocity. No? So it's what kind of frame? It is a inertial frame. The elevator's frame is an inertial frame because it does not have acceleration with respect to ground. So in this case, when you make the person's free body diagram, there are only two forces, mg and normal reaction, let's say n. So in this case, what is happening? And he is at rest in that frame. So n is equal to mg. So that is his true weight. Okay. And in the third case, here what is happening is that again the elevator's frame is the non-inertial frame, but having a downward acceleration of a naught. The elevator's frame is a downward. So on the person inside, when you make the FBD, the pseudo force is acting upwards now, and the normal reaction is upwards, and mg is downward. So in this case, in the third case, you will see that N2 is equal to true weight minus pseudo force. Okay. So this is when the elevator will be showing him, I mean the reading, the weighing balance will be showing him in the minimum reading. So now you substitute the data which is given in the question, and rest of it is very simple. So according to the data of the question, the maximum reading is N1. So N1 should be equal to how much? It should be equal to 72 into this thing. It should be 72g, whereas the minimum reading should be n2. It should be equal to the minimum mass it reads, 60g. Okay, because 60 kg is the minimum reading, whereas 72 kg was the maximum reading. Okay, so now we compare these equations. So mg plus ma naught is equal to 72g. Okay, and from here mg minus ma naught is equal to 66g. So from this you can easily find out that how much is m, and you can also find out how much is a naught. Both the things you can find out. Okay, so hope this question is clear, people. Now next we'll move on to question number 19 after this. So go through it. I'll explain question number 19's free body diagram. Yeah, so see Harsh, what is happening now, that you have to ask yourself that in which situation the reading will be maximum na? That will be in the situation when the pseudo force is acting downwards. तभी तो normal reaction ज़्यादा हो रहा है. And when the reading will be minimum, when the normal reaction is minimum, so for that time the pseudo force should be acting opposite to the acceleration. I mean opposite to the weight. So in which case the normal reaction is more than the weight, which case the normal reaction is less than the weight. So that is showing me that okay, in the case where acceleration of the frame is upwards, the normal reaction will become more than the weight. So that is when the reading will be maximum. Na? Whereas in which case the normal reaction will be less than the weight when it's decelerating while going upwards. So that is when the reading will be minimum. Understood now? So let's say you're doing the experiment and you're actually measuring the, the readings of this, you're noting down the readings of the weighing machine. So the reading will tell you that, okay, it's in one case you're getting very large reading, less, the other case you're getting a lesser reading than the true weight. So in the case where you're getting a larger reading, the pseudo force must be downwards. It must be pushing you down. So your normal reaction is increasing. So that's how you know that that is the case where the acceleration is upwards. Okay, so let's move on to question number 19. So we will learn about the concept of buoyancy in detail later in a chapter called fluid mechanics. Okay, but here we just need the free body diagram. We don't really need that much detail of buoyancy. Okay, we just need to understand that buoyant force is a constant force that is acting on the balloon, as it is in the two situations which are shown. So in question 19, basically you have to follow the instruction of the question to understand about the buoyant force. Buoyant force is the same thing as upthrust, or the force that you get from Archimedes principle. So air is also a fluid, na? So a balloon floating in air experiences upthrust or buoyant force, just like a block of wood floating in water or a block of ice floating in water experiences upthrust. So water is also fluid, air is also fluid. So what happens is, in the case of a floating balloon in air, the density of the helium inside the balloon is less than the density of the air around. So the upthrust dominates. So that's why it tends to go up. Just like the density of wood is more than the density of water. So if you push a block of wood underwater, it will tend to accelerate upwards. Because the upthrust that the water is applying from outside is going to be greater than the weight of the wood, because the density of water is more. So it will tend to get accelerated upwards. So that concept we have to use now here. So the question is saying that there is a force of buoyancy exerted by the atmosphere on the balloon is B in the upward direction. So buoyancy, or we can call it buoyant force, is B in the upward direction. Okay. In addition to this, there is also air resistance. So air resistance is something that acts because of the sort of friction that is there between the air particles or the air molecules or even dust particles in air with respect to the surface of the balloon. So it applies some kind of decelerating or resistive force. So air resistance force. So this is also described to us. Sometimes this is also called air drag. Okay. In aerodynamics, you will hear the term air drag. Okay. So it is the drag force or resistance force because of the friction between the air particles and the surface of the body which is moving through air. So air resistance force is given to us such that it acts opposite to the direction of velocity and proportional to it. Okay. So it acts opposite to the direction of velocity, and the magnitude of the force is proportional to the magnitude of the velocity. Okay. So it's like this. This is the air resistance force. Whereas this is the information about buoyant force. So now in one case, what is happening? The balloon carries a mass m and is found to fall down near the Earth's surface with constant velocity. So let's say this is the balloon and you have suspended some mass m. And what is happening is, in this situation, the balloon is falling with a constant velocity v but zero acceleration. Okay. So in this case, what are the forces acting on the balloon? The forces acting are the weight, okay, the buoyant force, and this one we'll call it FD, let's say, which is the drag force. Okay, so the drag force will be such that the magnitude of the drag force is proportional to V and direction of drag force is opposite to V. Okay, so we can say that drag force has a magnitude of some constant into V and has a direction which is opposite. Okay, so in this case, the velocity is downward. So the drag force will be in which direction? It will be upwards, and its magnitude will be some constant into that V. Okay, V and FD are in opposite direction. Now, in the second scenario, what you're doing is you're removing some mass from this. Okay, so let's say in the second case, some delta M mass is removed from the load M. Okay, so you remove it. So what you have left behind now is some lesser mass, let's say M prime, which is M minus delta M. So इसकी वजह से क्या हो रहा है now? Buoyancy is dominating, so it's going upwards, but at the same velocity and zero acceleration. Same magnitude of velocity, but zero acceleration. So now what are the forces which are acting? M prime G, buoyant force. Okay, and this time drag force will be in which direction? It will be downwards because the velocity is upwards. So that drag force will again be C into V because the magnitude of the velocity is the same. And the acceleration is zero in both the cases. So case 1 and case 2, you just make the two free body diagrams and you'll be able to figure out. So in this one, you're getting drag force plus buoyant force is equal to capital Mg. And in this one, you're getting buoyant force is equal to the drag force plus M minus, or we can just write this as M prime G and later substitute it as. Okay. And we know that delta M is going to be M minus M prime. So that's what we have to calculate. How much mass should be removed from the balloon? Delta M is what we have to calculate. So you can just subtract the two equations. Or we want to get rid of CV now, because the answer should be in terms of buoyant force. So do one thing, do equation 1 plus 2. So CV will cancel out and you will get 2 times the buoyant force is M plus M prime G. So that means M prime is equal to how much? It is M minus 2 times buoyant force by G, or rather opposite of that. Just 2 times buoyant force by G minus M. Okay. And that is equal to M minus delta M. So delta M should become how much now? It should become M minus. So delta M, the mass that you removed, should become 2M minus 2B by G. This is the mass removed. So this should be answered. Okay. So Harsh, hope the question is clear now. Okay, good. So you can try question 20 by the same method. Yeah, no problem. Okay. So what I will suggest is that you have asked question 20, but based on this now, you can try it yourself. Try according to the same method. Same type of free body diagram as question 19. Okay. Only in that there's no drag force. There's only buoyant force and weight. So that's why it's a little bit easier in fact. Okay. So in question 20, there is no drag force or resistance force, only buoyant force and weight. That's why I'm saying it will be a little easier. You can try it out yourself. Okay. So next we'll do question 21. Question 21 is a slightly different question because it involves the application of cross product. Okay. So we'll discuss in detail. You have done that, Bhargav? Okay, let me check. Okay. I'll try to finish the Newton's laws doubts and come to that then, okay? And by chance, if we cannot, then I'll send you the solution on WhatsApp itself. Don't worry. Okay, so let's come to question 21 fast. Okay, hope this one is clear. So question 21, it is given to us that the force acting on a body is given by this relation V cross A, where A is some constant horizontal vector. Okay, and V is its instantaneous velocity. Okay, so let's try to understand this. Okay, so this we'll have to visualize in a three-dimensional system. So let's say we have a system like this where my XY plane is this one, the floor space. This is my XY plane, and this is the Z axis, which is vertical. So this XY plane is the horizontal plane. Okay, and Z axis is therefore vertical. Okay. Now supposing, just assume that my vector A, which is a constant vector in the horizontal plane, supposing that is AI cap. Okay. So my vector A looks like this now. So in this diagram, my vector A looks like this. So now if I give a particle of mass m somewhere here, some velocity, okay, so I want that, V cross A should be vertically upwards now, because on that particle the weight will be acting vertically downwards like this. So if I want it to go at constant velocity, okay, so mg will be minus mg k cap, okay, that is vertically downwards. So for the acceleration of that body to be zero, the net force on it must be zero. So that means this external force that we have plus the weight must be zero. So this V cross A force that we have, that one plus mg should be zero. That means V cross A should be equal to mg k cap. It should be upwards. So I want this thing. I want that external force should be vertically upwards and equal to mg in magnitude. So I want that situation. So now to create that situation, how I have to give the velocity. Let's understand that. So I want that the external force, which is B cross A, I want that it should be mg in magnitude but opposite in direction. Okay. So you can see that to give it an upward to give it an upward force, we will need to give the particle a velocity which is in some direction like this. If we give the particle a velocity which is in some direction like this, and of course our A vector is like this, okay, and the angle between them is theta, then this force vector that we have, it will have a direction like this. V cross A's direction, you can see, will be upwards. Okay, but more importantly, if this angle is theta, the magnitude of this force will become AV sine theta. Okay, and what I want is that that magnitude should balance the weight. No, I want that situation that the net force on the particle should be 0. So the magnitude of this force should balance the magnitude of the weight mg, which is acting downwards. Okay, so I want that on this particle I should give a velocity such that the net force is becoming 0. So this situation. Okay, so from this diagram you can see that I want this situation that mod of V cross A should become equal to mod of mg, that is mg. So VA sine theta should be equal to mg. So V should be how much? Mg upon A sine theta. So if I want to project with the minimum velocity, then sine theta should be maximum. So V minimum will become mg upon A into sine theta ka maximum. Now sine theta ka maximum is 1. So you can see that the minimum speed with which you have to project will be mg upon A in the horizontal plane, such that this is happening. So that theta should be 90 over here. So this theta should be 90 degrees, so that sine theta becomes 1. Then B will be equal to V minimum, which will be equal to how much? Mg by A. So this becomes the answer. Okay, so this is the logic of this question. So bit of vector algebra and three-dimensional application of cross product becomes important. It becomes important to visualize that over here. So Harsh, once again, this was your question. So I hope this is clear, beta. Harsh, just go through this and let me know, confirm if it is clear. Okay. So see Harsh, what is happening here, na? जो force है body पे, जो external force है, that is given to us by this expression. Okay. It's given to us by this expression that it is A cross B. This is given to us, where A is a constant horizontal force. So मैंने अभी क्या assume किया है that A is a, like, first of all I have taken my coordinate system such that the XY plane is horizontal and A is lying along the X-axis. Okay. So when I look at this from top, now it will look like this. If this is my X-axis, this is my Y-axis. Okay. So in this, if I assume that my vector A is along the X-axis, then if I take a particle from here and project it with a velocity V like this, okay, then what is the direction of V cross A? You can see that is coming out of the plane, no? So V cross A will be coming out of the plane. So for this n cap will be out of the plane. So that is along which axis? Z axis. So that is in which direction now? It is vertical. Right? So that's why in this three-dimensional thing, if I've taken V like this, the direction of V cross A is coming out of the plane in this diagram. That means it's vertically upwards over here. And the magnitude of this is what? It is. So this becomes BA sine theta n cap. No? It becomes BA sine theta n cap, where because it is coming out of the plane, so my n cap will be what? K cap. Okay. Whereas mg is what type of force? It is minus mg k cap, no? Because it is going into the plane. Okay. So now I want that this F and mg should cancel each other. So F should be equal to minus mg. No? So that's why I want that the magnitude of that should become like this. Just a moment, guys, that will come back on the screen. Okay. So Harsh, is this clear now? Okay. So now what I want is that the magnitude of F should balance mg. Direction is already opposite. Now we have seen that mg is and this are in opposite direction. So this means this. So magnitude of F kitna hai? It is AV sine theta. So that should be equal to mg. So that means V in general should be mg by A sine theta. Now the question is asking what is the minimum speed with which I should project so that the acceleration is zero. So for the minimum condition, I should select my theta such that V comes out to be minimum. So I should select my theta to be 90 degrees. So sine theta in the denominator becomes maximum. So my magnitude of velocity becomes minimum. So that's how I'm getting the minimum speed of projection to be mg by A. It should be projected with this angle theta here 90 degrees so that the V cross A wala jo F force hai, that is balancing the weight. Is it clear now the solution? Okay, very good, Beta. So this is done. Now we will move on towards the more complicated questions. So next doubt I've received is question number 33. But I just want to ask anybody has a doubt in question 24 or 28. Please go through it and let me know. Okay. If you don't have a doubt, it's fine. If you've done these questions, it's very good. But if you have a doubt, let me know these two questions. Otherwise, we'll move on to question number 33 next. Yeah, Harsh, so 28th question, let's discuss. So let's come to question 28. So these masses are given. So it's asking how long before M1 strikes the pulley, and that distance is given 20 centimeters. So basically we have to find the acceleration of M1. We have to find E, let's say, which is the acceleration of the block M1 in the diagram. I'm quickly making the diagram. So we have this pulley here. Now this is attached to the ceiling. Going around this is one thread. Now that thread is going to be attached to the axle of the second pulley. And then of course another second thread is going around the second pulley. Now we have all these blocks. Okay. So this is our M1, this is our M2, let's say, this is our M3. So these are the blocks which are all connected. So of course this pulley is attached to a fixed ceiling. So it's P1 is a fixed pulley, it does not move. Okay. But the second pulley P2 is going to move. Okay. So that's where we have to understand the dynamics of the system. कि अभी देखो यहाँ पे this M1 mass is minimum out of the three now. M1 mass is minimum. M1 is 1 kilogram, M2 is 2 kilograms, M3 is 3 kilograms. So you can see this side, the right side of the pulley P1 is attached to more heavier things than the left side. Okay. So definitely what will happen is that this block is going to go up with some acceleration here. And that's why this length is given to us. So we have to find out how much time this will hit. So that time will come like this, that half et square is equal to L. So from that we'll get the time when it hits. Okay. So basically we need to find E. Now you'll understand that this pulley, because it's attached with this thread now, it's coming down with the same acceleration. So first thing, if M1 accelerates upwards at E with respect to ground frame, okay, then the pulley P2 has acceleration E downwards again with respect to ground. Okay, that's one thing. And the other thing is, now in the frame of this pulley, this one will have some downward acceleration, let's say A prime. So this one will have the same magnitude of upward acceleration A1. So now secondly, with respect to the pulley P2's frame, which is basically a non-inertial frame because it's coming down with an acceleration A, M2 has an acceleration of A prime upwards. So that means M3 will have an acceleration of A prime downwards. Okay. So now next what we'll do is we'll make the FBDs of M1 in ground frame, that is inertial frame, but of M2 and M3 in the pulley P2's frame, where it is at rest, where I mean they are having common magnitude of relative acceleration, but that's a non-inertial frame. And once we made these FBDs, we will solve for E. Okay, so that's what we have to do. So Harsh, hope you understood the question now, how we have to solve this. Okay. So just note this down and start making the free body diagrams. I'll make the FBDs in a minute or so. Okay. Just try to make the FBDs yourself without making a mistake first. Yes, Bhargav, that's correct. That's why this parameter is na A prime, and that one is A. So obviously A is not equal to A prime. You can take it as A1, A2 also if there's confusion from that. Yeah, sorry, the screen has gone again. Yeah, so one more thing we have to be careful about here is the tension. So you'll see that if this thread has a tension T, okay, then this second thread here will have a tension of 2T. Why? Because the pulley P2 is massless. So you have to also understand that this tension, suppose it is T2, it will be 2T because this pulley is massless. Okay, so that's one more thing here. Okay, so this tension T2 will become 2T because the net force on it must be 0, like that one needs. Okay. So we have to be careful about that also. Okay. So on this one, the upward tension that is acting, that is that tension T2 in that string, let's say, so that is 2T. Okay. And its own weight M1G, and it is having an acceleration A upwards. So we have the equation that 2T minus M1G is equal to M1A, and substitute M1 as 1 kg. So we have 2T minus G is equal to E. That's our equation 1. Okay. Now you make M2 and M3's FBD in the non-inertial frame of the pulley P2. So that one is coming down with this acceleration E. So with respect to that pulley, M2 is going up with A prime and M3 is coming down with A prime. So A prime is the acceleration of M2 upwards or of M3 downwards with respect to the pulley P2. Okay, and in that frame you can see the forces acting on this are tension, okay, weight, okay, but also pseudo force, and the pseudo force's direction will be what? Opposite to E. So it will be M2A upwards for this, M3A upwards for this. This is the pseudo force. Okay. So for these two now, we will have the equations. For this, we'll have the equation T plus M2A minus M2G is equal to M2A prime. And substitute the value of M2 as 2 kg. So we have T minus 2A minus 2G. Oh, sorry, T plus 2A minus 2G, yeah, is equal to 2A prime. So this is my second equation. Okay. And for this one, we'll have the equation the net downward force, which is weight minus tension minus pseudo force, is equal to mass into this acceleration. Okay. So now substitute M3 as 3 kg. So we have 3G minus T minus 3A is equal to 3A prime. So this is our third equation. Now we have to solve these equations for the value of E. That's the thing we were interested in the question. Yeah, Harsh, you understood the tensions why they are 2T and T. Okay, good. So just make a note of this and you can finish off solving the equations we'll discuss. Okay, so what you can do is now between these two equations, you can eliminate A prime. Between equation 2 and 3, you can see that equation from 2 and 3, you can see A prime according to equation 2 is T plus 2A minus 2G divided by 2. And from equation 3, it is 3G minus T minus 3A divided by 3. Okay. So T by 2 plus A minus G is equal to G minus A minus T by 3. Okay. So T into 1 by 2 plus 1 by 3 is equal to, oops, how did that happen now? Just a moment, guys. So anyway, it appears there was a bit of software glitch. So I have got to do some work again. Anyway, so T by 2 plus A minus G. On the other side, this will become G minus A minus T by 3. Okay. So if I take tension on one side, I have half plus 1/3. On the other side, I can take 2G minus 2A. Okay. So this tension will come out to be 6 by 5 into 2 times G minus A according to this. Okay. Now compare with equation 1. So you'll get the value of A. So from equation 1, you can see that T is equal to A plus G by 2. Correct. So substitute that here. So from equation 1, T is equal to A plus G by 2. So that should be equal to this. It should be equal to 12 by 5 into G minus A. So A into half plus 12 by 5 is equal to G into 12 by 5 minus half. Okay. So A into 5 plus 24 should be equal to G into 24 minus 5. So this A should come out to be 19 by 29 G. Okay. So therefore now you put that L as 20 centimeters or 0.2 meters and half AT square equal to L. So from that we calculate the time. So you have to be a little like, you have to practice out solving these type of simultaneous equations also. If you're not that familiar with them, that is just the maths part. Okay. So I'll take you to the top of the equations once more. Make sure you understood how we got equation 1, 2 and 3, and then below this is just the solving part. So finish this off and then go through question number 33 next. We'll discuss in detail. It's an important question. Okay, so hope this question is clear to all of you guys. Okay, now let's move on to 33rd question. I told you that's an important one. Now 33rd question, like the same technique we have to use that we've done in another question, related to how pseudo force can prevent a block from slipping on this inclined surface, because the inclined surface is on a wedge which itself is accelerating. So if there's sufficient acceleration for the wedge, then the pseudo force acting on the block placed on the wedge will prevent the slipping from occurring. Okay, so that is the concept we have to use here. So we have this one whose mass is m, this one whose mass is m prime, this angle is theta, this surface is smooth and all that. But now we are also placing a block here of mass small m, and we want to find, so given that we know the value of m and we know the value of m prime, we want to find the value of capital M such that, and of course we know the angle theta also. Okay. We want to find the value of m prime such that uh, the block small m does not slip down the inclined surface of the wedge m prime. So I want this situation. Okay. So why I said this is a similar situation to one question we've done, because if you put the correct amount of mass here, this will have an acceleration such that this whole system will have a common acceleration of E. This whole system will be moving such that this is at rest, this will be at rest with respect to the wedge. Okay, so what we'll first do is we'll make the free body diagram of the block, the small one, in the non-inertial frame of the wedge m prime. Okay, and find the value of E such that the block is in equilibrium in this frame. Okay, so like that. So when I make that free body diagram, it's in this frame of the wedge, which is moving with an acceleration E. So on that block, there's going to be pseudo force, which acts like this. There's going to be its own weight, it act downwards. And remember, this is a frictionless surface. So this is also smooth. This is also smooth. Okay. And there's going to be normal reaction, which acts like this. Okay. And under the action of these three forces, it should be at rest in this frame. Okay. So now we know that this angle is theta, as is this angle theta. So we have that along our x-axis, if we want to balance the forces along our x-axis down the inclined plane, we'll have to see that mg sine theta down the inclined plane balances ma cos theta. Okay. And along the y-axis, of course, normal reaction balances mg cos theta plus ma sine theta. So this equation is not so important. The first one is more important. So we're writing this down. So see what the first equation is now telling us. The first equation is giving us the value of E. And this is the same thing we had done earlier also, that how much acceleration is required. So that part is the same. That acceleration will come out to be g tan theta. E should be equal to g tan theta for the block to not slide with respect to the wedge. That is the condition for this. Okay, so note this down first, and then we'll make the FBD of this capital M1 to find out how much mass is required so that this acceleration comes out to be g tan theta. So this will give us this. Okay, make a note of this please first. Okay, so hope the calculation of this g tan theta is clear. Okay. Now next thing, we have to find the value of m so that this acceleration is g tan theta. So this tension is T in the thread. You just make two free body diagrams. One is of the block, which is hanging vertically. So now make the FBD of this block, which is hanging vertically. So on this, there's tension T, weight mg, but we know its acceleration A downwards should be equal to g tan theta for the condition that is given to us. Okay, that. So we get mg minus T is equal to ma. So that's another equation that we get. Okay, and then make the combined FBD. This is in inertial frame only. Then make the combined free body diagram of the wedge plus the block because they are having the common acceleration. So this is the same trick I told you earlier also. This whole thing is having a common acceleration A in the ground frame or in the inertial frame. So on this, the external force is only this tension, the combined weight m prime plus small mg, and the normal reaction from the ground. The contact force between these two need not be taken because it's an internal force. So on the horizontal direction, we have the equation is T is equal to m prime plus m a. That's our fourth equation. So now between these two equations, substituting the value of this, okay, we will eliminate T to get the value of this. Okay, so from this we can see that T is equal to mg minus ma. Okay, and from this that is equal to m prime plus m a. Okay, so that will give us the value of m, which is an unknown quantity. So capital M, which was the unknown quantity, should be capital M prime plus M into A upon G minus A. And now just substitute this. So get this as tan theta upon 1 minus tan theta because you will substitute A as G tan theta. Substitute that. So that becomes your answer. This is what your capital M is. So hope this is clear, people. Now this they have written in a slightly different way in HC1. No? They have written it in like this can be written as 1 upon cot theta minus 1 minus 1 by cot theta. So taking the LCM in the denominator, this will become this. But that's basically the same thing as this. There's just trigonometry between this step and this step. So that's another thing you have to be alert about here. Okay. So anyway, I'm just taking you to the equation solving part once more. So you got A equal to G tan theta that you saw. Now you see the individual free body diagrams of the block and the combined FBD of the triangular wedge plus the smaller block. Okay, so hope this question is clear to all of you. Now with this, you should be able to complete the remaining questions in HC Verma. Okay. We'll keep some time aside for doubts to complete HC Verma the next lecture also. But by and large, now we will start with the next chapter after this. Okay. So finish HC Verma and clear your remaining doubts in the next lecture, surely, so that we can proceed with the next chapter. Also, from your module, you start doing questions. The module exercises has question of Newton's laws of motion and friction together. So we will basically do those questions once friction is completed. But you can start picking out the questions which have smooth surfaces without friction and start solving them already. So the same concepts that you're seeing here will be applied in that. Okay? So that's it for today's session, people. Wish you all the best. Acha, Harsh, you're writing. I'll just minimize this for you. Yeah, is it all right now? Okay, so that's it for today, people. Wish you all the best. As I said, complete HC Verma. Anything pending now, just send me the doubts. I will discuss.